insulator and ferrotic material. And so what I want to discuss is the interest of these Edelstein effects. What is, okay, 5 minutes is okay for me. Thank Carlos. So what is difficult in the comparison that here we have a production of two-dimensional sharp current from a three-dimensional sharp currents, and this here there is a coefficient between two three-dimensional currents for the spinel effect. But to have the same, to compare, is necessary to integrate this current density, three-dimensional current density spinel effect over the total thickness of the platinum layer, and integrating, making this integration will obtain the two-dimensional sharp currents. And it appears from the calculation, classical calculation, that now the equivalent of this lambda is a lambda star, which is the product, the maximum two-dimensional current that can be produced by a thickness larger than the spinel length in the best condition. The equivalent of this lambda is lambda star, the product of the spinel angle by the spinel length. And so it's necessary to compare this lambda, for example, 2 nanometers for alpha T, and this lambda star, and what I did on the next slides. To calculate the gain in sharp current for the same injected spin current density from spinel effect, platinum, tungsten to alpha T. And so alpha T characterized by this lambda here. And for example, platinum characterized by this theta and this LSF. And then one sees that in fact there is always a large advantage, a factor of more than 10, going from platinum to alpha T, or going from tungsten to alpha T. The enhancement is by a factor of, depending on the experimental data you take for tungsten, from 4.5 to 8. So there is an advantage by more or less one order of magnitude. And if we consider now the gain in electrical power, yes, then the gain will be much larger, because if you consider the electrical power, the best condition is what is involved is also the impedance of the resistance of this resistance of the two-dimensional. And the resistance of a two-dimensional state is always much larger than the resistance of a layer of platinum, of a layer of tungsten. And then, so if I take this value we have for alpha T, for the interface resistance, resistance per square, and the corresponding value for the best condition for spinel effect is when the thickness is exactly the spinel length. And so we have to compare again with and then the efficiency, the enhancement is much larger. So 10 to the fourth, if one compare alpha T and platinum, and 10 to 3 to the third for comparing platinum. So in fact, for this sort of application, there will be again a much stronger advantage for, and if one consider also the inverse effect, and that is characterized by this coefficient Q. You can see value of Q 1 nanometer minus 1, according to the group of Otani, paper by Fondu. These are suppose. And then again, if one compare also the efficiency for the opposite conversion, one obtain also relatively large factors. Okay, I don't want to discuss, in fact, so we published recently with Schuffenzang a theoretical paper on the compare theory of the inverse Edelstein effect and inverse Edelstein effects, but I don't have the time to discuss. And I will finish with a small rapid comments. In fact, as I have said, topological insulator could be very efficient for this conversion effect, for the conversion, creation of spin currents or detection of spin currents. And of course, the best would be if it can be also tuned by some, for example, electrical voltage. And in fact, one of the possibilities is using hashbar systems we are also ferroelectric, because the ferroelectricity first induce the inversion symmetry, producing the hashbar effect, and then also reversing the ferroelectric polarization okay. And so I will simply comment the last, and this is this system we are studying. This, in fact, we are only at the end of the chain of results. This system is mainly studied by this group in Milan. And so what they have already shown is that there is a hashbar splitting. This is, for example, and the hashbar splitting depends on the direction of the polarization, of the ferroelectric polarization, and also there is also a strong spin polarization of these hashbar states. And so we are just beginning this some spin coupling experiments, and we have already some preliminary results showing there is a inversion effects, but for the moment we have no gauge and we cannot see that we can change this signal by simply inversing the polarization. This is okay, my summary. I suppose that Carlos, I am meantime. Okay. So it's not my summary. So if I want to summarize my the talk, so I say general conclusion: they are spin-orbiting two-dimensional systems, hashbar, topological insulator, LRO-STO, are much more efficient than in 3D systems, bulk system, spin-on effect, for spin charge conversion and spin-on device. What is topological insulator can work at room temperature. In fact, in most systems, they do not work in room temperature because there is a shunting at room temperature by a non-perfect insulating bulk topological insulator. And the other conclusion that the topological insulator can be even more efficient if the topological two-dimensional states are protected by an interface with an insulator. And so last is I thank to the co-worker of this work. All the things on the business silver, topological alpha-tin has been with this co-worker mainly in the frame of this ANR, the national project, and you can see the photos of the group. And for LRO-STO, we have, you can see also the name involved in LRO-STO, and the collaborator, the co-worker in Milan or in Germany for German Tellurium. And so I thank you for the attention.
Thank you very much, Carlos, for the nice talk and for the time. So now we have questions.
So have you used this business silver to stage?
No, we did not. We transferred on to the consideration. But what somebody, okay, I suppose that you have some results.